Our next presentation is all about NMOS, the wonderful control protocol that was developed in conjunction with ST2110. We have an expert speaker here, Deame, the CEO of Nextera Video, and he's going to be talking about NMOS. Can there be one control system to rule them all? So welcome, Jed.
Okay, thank you, Wes. Thank you, everybody, for coming today. So I've got a bunch of material. I'll be going through probably pretty quickly, but feel free to stop me if there's something you want any more detail about. Here's the outline. So we're going to start with what is NMOS, what are the required pieces, what are some of the optional pieces that some people might want to add to their products or systems, what are the new things that are under development that we're meeting weekly to discuss in the activity groups, and why do I care about all this, and is it going okay, and finally, how can I try it myself? So let's jump right into it. So what is NMOS? Well, it stands for the Networked Media Open Specification. It was developed by a group called AMWA, the Advanced Media Workflow Association, and the intent was to deliver an open system for control of IP-based products, particularly 2110, to allow one control system for basically doing the routing. In the SDI world, remember, we had a different control system for every vendor's router, but we didn't want to do that in IP. We said, let's just have one system that everybody uses. So that's, in essence, what the NMOS system does. So it allows us to seamlessly interoperate, and that's really the trick. Originally, when 2110 devices came out before the NMOS was ratified, it was a lot of typing in IP addresses and doing drivers for each specific device, and that was just very painful, very time-consuming, not really a good use of anyone's time. So we said, well, how can we make this plug and play? Well, how do we take it beyond what we had in SDI and make it plug and play and auto recognizing of devices and as easy as push button simplicity, but with the benefit of having automatic discovery, much like you have when you plug in your printer. You don't have to go into your PC and tell it what COM port you're on anymore. It finds it automatically on your network. So that's exactly what we're trying to do in NMOS. So how does it work? Well, we've got a cloud in the center, which represents our IP switch. All of our video sources are going into it, and our syncs are hanging off of it. So we've got a couple cameras on the left in this example, and we've got a monitor on the right. So what happens when you first power up the system, all the devices connect to that registry over there, which is a PC running some software and identifies themselves. Then the control panel, as soon as that happens, he can go query that registry and say, oh, I see I have two cameras here. I've got maybe a Sony and a Panasonic camera, and I've got a display, and it can even present those on the buttons if it likes. The control panel could put the name of the device that's there. So then a user says, okay, well, I want to do a route. I want to do a destination source take, just like you would in the SDI world. But a couple things happen in the background. There's a few layers of software that are involved. So first, what it does is it tells the next source, the current source to disconnect. So that X means disconnect that stream from the sender 1 to the receiver. So let's say it's already connected, and then it tells the switch through this protocol called IGMP, Internet Group Management Protocol. It says, I want to subscribe to that second camera on the lower left. So it's all done in the switch. So the receiver tells the switch, I want to listen to these streams. All these streams are coming in, blasting away at the switch, and the switch is just holding them until somebody asks for them. So that's what NMOS does. It says, please give me stream number 2, disconnect me from stream number 1. Make sense? Sound reasonable? Okay, good. Okay, well, so how does this all access? This is a control protocol we discussed. It's an API is what software people like to call it, application program interface, but really in plain English, all this is a series of HTTP commands, much like you would run in your web browser. If you browse to a website, you're doing a HTTP GET of that URL, right? So in this case, if I want to read a status of an NMOS device, I do an HTTP GET to the IP address of that device / xnmos / the thing that I want to read or access, the API name. If I want to command it somehow, like to do an activation, meaning to do a switch, then I do a put, an HTTP put, which is a write to that IP address. IP address / xnmos, like I might want to write to a sender, I might want to write to an audio map, I might want to write to a secure port. So it's a very simple interface. You can do it from the command line if you like, using there's a command called curl that you could type on the command line in most Linux and Windows-based systems, and just type these commands. You can go into your web browser and browse directly to the XNMOS resource names, and you can look and see, has this device shown up on my network? Is it in the registry? You can learn a little bit about it. So pretty simple way to access it. So what is a typical implementation? Say you're a product manufacturer and you want to add NMOS and or 2110 to your device. What does that look like? Well, here's a picture of a typical product. It might be, let's say, a gateway, an SDI to IP gateway or something like that. In the lower left, it's got the 2110 FPGA cores. Most of this done in FPGA. It can be done in software, but typically it's done in FPGA. And then, that's doing the stream management. And then on the far right, you've got the PTP, which gets your timing all lined up. And the piece we're really talking about today is the upper left, the NMOS core, which is a software core that's something that our company provides in addition with the 2110 pieces. But what that allows you to do is connect commands that would come from a controller down into your FPGA hardware to tell it what to do. Tell it, I'm going to listen to this stream, or expect a stream coming in that's 1080p50, expect this kind of colorimetry. All those things would come in through all these node APIs, all these / sources / centers / receivers. That's references the previous slide. This is how we tell it to do it. And then that activates the device, which is in the upper right. A camera or a graphics system or something might be sending content in or out. That allows the content to come into the FPGA and do the processing. Okay, so let's jump into, that's kind of the overview of how this all works and how it ties into 2110. So what are the required components of NMOS? First, I have to define what does required mean. Well, you probably have heard of the EBU. They actually made this document called Tech 3371 that says, here's our technology pyramid. Here are the minimum requirements for an AV over IP system. And as you can see, it's got listed all the basic NMOS pieces, the ISO 4, ISO 5, ISO 7, 8, and also ISO 9. And we'll go into detail about what all those are, but this is what I mean by required components. EBU says you should use these because it's going to make your life a lot easier. Okay, so let's start at the beginning. ISO 4, this is the first part that was developed. It's the registration and discovery. This is the plug and play piece I was talking about earlier. How does my control system know that I've got a device out there? Well, there's this language specified through ISO 4 that says, well, if I'm a node, I can talk to this thing called the node API, and I can tell it I'm a camera, I'm a monitor, this is my IP address, this is my colorimetry. If I'm the registry, which is, remember, this database sitting off to the side that's holding all this information, I've got a registration port or API, and I've got a query port or API that you can actually access from any device, from your PC, from your web browser. You could go into that query API and, again, through an HTTP read on your web browser and see all the devices that are on the network. Very handy, very, very nice for debugging a system. You don't have to run around and see who's turned on and who's actually working. So that's kind of the first step of it, is how do I register everybody on the network, put them in a database that anybody can see, a controller can see, or an operator that's trying to debug the system. Then, okay, I've got everything in my system. Now I want to do a connection, a switch, which we actually call activations in NMOS. That's what ISO 5 specifies. Here's the protocol of the command that I have to send from my controller to my sender and my receiver to say, please connect A to B. So normally it's just telling the sender, turn on your stream, and then it's telling the receiver, Here's the SDP file, the session description protocol file of the sender that describes all of its capabilities. Please configure your hardware to lock to that, and then tell the switch that you want to do this IGMP join. And there's three ways we can do an activation. We can do what's called an immediate activation, which is says now, switch right now, this instant. Or you can do it time-based. You can say switch it in 5 seconds, which is a relative time, or you can do an absolute, switch it 12 o'clock or 1 o'clock at the next show. So it's a nice way of automating some of the capabilities. Again, things that weren't really built into any SDI control protocol that are part of this NMOS. So that's your basics. I've registered my devices, I can switch them. Okay, and that's kind of where we started. But then we said, well, and we need to take it a little bit further. What about, tally, right? Well, I've got IP devices. I'd like to have a replacement for the, the traditional wire-based tally system. How do I do tally over IP? Well, that's what the next one, ISO 7, does. So tally, for those of you that don't know, it's a way for your switcher to, for instance, tell your camera to light up the tally light on top that says I'm pointing this camera at a particular talent in the news set, and I've selected that camera so the news anchor knows where to look. So there's a detailed protocol here that allows us to send these events or these tally indicators over IP just as another packet using the same ISO 5 connection mechanism. And it can be done a few different ways. MQTT or WebSockets are kind of the low-level details about how that works, and there's pros and cons to each of those, but it's got mechanisms to support that GPIO over IP. Next, something else that we didn't really have in audio, in SDI rather, is audio mapping. That's ISO 8. That says, in SDI, we had to add boards to our routers, embedders and de-embedders, and we could add a bunch of extra hardware to do audio shuffling. But in IP, you don't have to do that because the video and the audio and the ancillary streams are all set separately. So you've got all your audio streams kind of bouncing around in the network. So it's not too hard to actually be able to do a channel mix. So that's what ISO 8 does, is it allows you to specify your inputs and your outputs and a map of how those connect. So I'll give you an example, make it a little bit easier. This is a demo actually we did a few years ago at NAB to show how the ISO 8 mapping works. We had a bunch of senders and receivers, and what we're trying to do is map the inputs on the left, which actually come from two different senders. So I've got sender 1, channel 1 through 8, and then sender 2, channel 1 through 8. So I've got two different audio senders out there, but I want to map those to an SDI embedded audio output, which would be the top. So I've got 16 channels in my SDI stream along the top. And what this diagonal pattern is doing, just by clicking those boxes, it's doing an invert. It's saying I want to take the last channel that comes in and put it in the first SDI output and vice versa. So what you can see the effect is the source was this harmonic source in the upper left that had decreasing audio signals, signal strength from two sources going diagonally down, and then our output, the Nextera gateway demonstration box on the right, which has it inverted the other way. So it provided the ability to map any input to any output. So nice little feature that we didn't have automatically in SDI. It doesn't cost you any more wires. It's just an extra layer of software. Okay, and the other nice thing that NMOS brings is this ISO 9, which is the system resource. When you start deploying 2110 systems, you quickly realize there's a lot of information that has to be entered into each product. You have to tell every single product what the PTP domain is. That's not fun. If you've got 100 or 200 or 500 different products, you have to go in manually and type that information in the old days before NMOS. Well, now with NMOS, we're saying, well, why don't we take this information that has to be, that every device needs to be told, and we'll just put it in a little system resource, little database. We'll have just a little program running on a PC somewhere that holds things like the PTP domain, the heartbeat intervals, like where do I want my syslogs located, for instance, for storing debug information. What protocol am I running? Am I running secure? Am I running non-secure? These kinds of things. And one other cool thing is this thing called System ID, because you can imagine if you have a node, a product, let's say a gateway or a server, it's in one IP system and the power goes down and the power comes up, what do you want to do? Well, normally you want to wake up the way you went to sleep. If you're transmitting a stream, you want to keep transmitting. But what if that box was powered down and moved to a different system and powered up? You don't want to be transmitting again. You're in a totally new system. You don't want to be flooding the network. So what it does is it sees, every device looks at this as, well, my system ID is 17. It stores it in some non-volatile memory. It goes to sleep. It wakes up. What's my current system ID? Oh, it's still 17? Great. I'll wake up the way I went to sleep. I'll start transmitting. Oh, but now I'm in system 23. That's a different system. Okay, I'm going to turn off my transmitter, or I might do a factory reset. You have a couple options. So it's a convenient way, again, to try to give you a little more plug and play and ease of moving systems around. So those are the required components. That's what every NMOS system, according to the EBU, should really have to actually make this work. What are some of the optional components? Let's jump into those. One of them is ISO 6. I won't talk too much about this, but this is just a different way of doing switching instead of IGMP. It's using SDN, software-defined networking, where the switch is actually being programmed by the controller to switch a stream to a different destination. Whereas in our typical system, IGMP, it's the receiver that's asking the switch for a stream. So this never really caught on because turns out IGMP can handle thousands of streams, so you don't really necessarily need this. It's some extra complexity. It does give you a lot more control. So if you're willing to absorb a little more complexity and you want to be able to have complete maps of your system and you want to do bandwidth reservation, it's kind of a nice thing to have. Topology discovery, those things, but most systems just rely on traditional IGMP. So this is kind of an illustration of that. In the IGMP world, it's the receiver that's asking for the connection, whereas in the ISO 6 world, it's the control system, the NMOS controller that's telling the switch to do the connection. Okay, then we have this other thing. There's a bunch of these BCPs, these best current practices that are part of the NMOS library of specs that just make life a little bit easier. This one, 002, is called grouping, and that allows you to say, well, since I have separate audio, video, and ancillary as 3 separate streams, it'd be nice if I could tie those together logically and say, well, these are all coming from server 1. So that's really what this does, and it's a common, so you could name this, right? You could name these groups. So I have a group called Playout Master that's got a video, audio 1, and audio 2. And you could also have these things called roles. So I could have a role of primary or 2-channel audio or 6-channel audio. It's just kind of a nice thing that you can set in every node. You can define these groups that when your controller connects to you or looks at your registry entry, it can see this and it can present it to the user. And it can just give you like one button to route video, audio, and ancillary for that whole selection. Okay, let's talk a little bit about security. So, as you move to IP, that's always the first thing that an end customer starts to worry about. How do I protect my content? How do I protect my distribution system from bad actors that are trying to do things I don't want to do? So the NMOS security group came up with a bunch of goals, talking to a lot of end users, like what are you looking for? What are the things that are important? So, one is confidentiality. How do we make sure that the data passing from A to B is unreadable by other third parties? 2 is identification, which makes sure that the API knows it's acting with a trusted authority. 3rd is the integrity. Make sure that the data traveling from A to B hasn't been tampered with. And finally is authentication, that makes sure that packets going from one API are coming from the API that expects and not from somebody else. So how do we implement this in NMOS? Well, there's a bunch of these BCPs, 003-123. Number 1, I would say, is the most important because it solves the first problem of taking the communication from the unsecure mode to the secure mode. Much like your web browser, you notice most websites now are HTTPS. If you have one that's not, you get a nasty warning in your browser saying this site is unsecure. Well, that's what this is doing for NMOS. It's saying, let's not just do an HTTP put or get, let's do an HTTPS put or get. So now it's encrypted going from A to B, so someone in the middle can't be listening in. If you don't have a certificate, you can't actually issue a put or get. So that's the most important one, and that we actually just did interop testing of that at the JTNM event 2 weeks ago, and that's looking really good. We've already got solutions available for that. If you want to take it a step further, you can do authorization, which is 00302. So, first remember, authentication is, am I a legitimate device that's allowed to talk to this other device? The second is authentication. Me as a user, I'm logged in. Do I have permissions to do a particular thing? So that's the authorization. And then the final one is certificate provisioning, which is because certificates sometimes can be a pain to distribute. So we've come up with a way to do automated certificate distribution so that you've got trusted sources. Okay, and then we have IS-10, which kind of ties this all together with this authorization built around some industry standard techniques like JSON Web Tokens and this OAuth authentication system. So let me just step back a little bit and talk about the underlying structure of how this all is protected. This is a system called PKI, Public Key Infrastructure, and the way PKI works is you've got a way where you can provide these keys, public keys and private keys to protect data, and this is the way web traffic is protected, and this is the way secure NMOS is protected. So let's say Bob would like to send a secure message to Alice. Bob would encrypt that information with Alice's public key. So this is a key that she just openly can distribute. That's fine, anybody can see it. So if you want to send Alice a message, you encrypt it with her public key. Great. But she's the only one that can decrypt it because she protects her private key. She's the only one that can see that, so she can send those messages through. That's the same way that's the way basically HTTPS works. So that's a lot of talking about how it works. Let's just show you a picture. It's a little bit easier to absorb. So I've got a broadcast controller. I've got a source and a destination. I want to send securely. I want to command data to go from the source to the destination. Well, there's one new piece added to the system called this authorization server. Again, it's another PC or the same PC running another piece of software. And the way it works is the controller, your button panel or whatever your control system is, before it tries to do this activation, it says, hey, Mr. Authorization Server, I have user 1 that wants to do this thing. It's a request. Can I do it? And he comes back and says, yes, they're a valid user. They're authorized to do that particular switch that you've asked for. So he sends back this token, this JWT token. And then the controller uses that token to tell the source to start transmitting. Source says, well, wait a minute, I don't know, how do I know that's a good token? Let me compare it against the public key of the authorization server. Okay, yes, that's a good token. I'm going to start transmitting. Transmits it to the switch. Again, it stops at the switch until somebody asks for it. Now the controller tells the destination, hey, here's the same JWT token. Please subscribe to this source stream. He says, wait a minute, is that legit? Yes, it is. I compared it against the public key. Great. Now it all happens. So this is a question. Yes, sir. The switch isn't drawn in here. Yes, sir. Yes, the traffic all goes over the switch. That's what I was trying to show with this little half arrow here. The arrow stops at the switch, and then when you subscribe to it, then the switch lets it through. Okay, I should probably put the switch in to make this more clear. Thank you. Okay, so this is just a slide that lists a bunch of these secure technologies. I won't review these. These will be in the recording if anybody wants to look at them. These are all the cipher suites that NMOS uses, different levels of encryption. This is, again, just a reference. It'll be in the recording if someone wants to see what all these acronyms mean. So let's talk a little bit about the future and kind of come back to the title of the presentation. can there be one control system to rule them all? Because what we've talked about so far is really just basic switching control, not device control. Just, it's just routing. So, so how do we take it a little bit further? Well, the first way to extend NMOS is to be able to handle different types of content. So in this case, JPEG XS. So JPEG XS is used sometimes to compress 4K to get it into 10 gig. It's used in the Pro AV market to compress it all the way down to 1 gig. The controller kind of needs to know that, right? If you're going to try to route one sender to one receiver, it needs to know if they're compatible with each other. So that's what this BCP006 does, is allows you to present information about each individual device. I'm either RAW or JXSV, JPEG XS video are the two common options, but they could also be other codecs. And it just uses all the other fundamentals that we built upon that we talked about, ISO 4 and ISO 5, and updates to the SDP file to make this happen. The next one is stream compatibility management. How do we do things like in the HDMI world, we have EDID, which says, Mr. Monitor, what resolutions do you support? And let me advertise those to the rest of the world so that I'm not trying to send you a stream that you're not compatible with. So we're doing the same thing in IP. We're allowing you to advertise to the registry the formats that a receiver supports. And that could be dependent on the display that it's connected to, right? Maybe a receiver can handle 50 hertz and 60 hertz, but the display can only handle 60. So, you can actually use the EDID capabilities to look at the display and then advertise those using this BCP004 receiver capabilities mechanism. Again, these are just other APIs. This is just a place that you could browse to with your web browser, or the controller can browse to and read a little data file that says, hey, here's what I'm capable of. Here's my video format, my frame rate, my color sampling, my SDR, HDR capabilities. And then this BCP005 specifies how I can map my EDID information into that. So nice little handy piece. So here's kind of the where this is all going long term is IS-12. How do I go beyond just informing switching and be able to actually control a device? Because you've got now one API. It's nice that it's one common API for switching, but every device I need to talk to, my control system needs a driver for. I need to talk to a camera or a graphics unit or a switcher. Everybody has their own control protocol. Well, why not have a universal protocol? And there's a lot more work to do to make this happen, but that's really the goal here, is a common protocol so that any device will speak this same language, this NMOS device protocol language. And so it's intended to be a replacement for some of the commonly attempted ways to do this, like SNMP was a first attempt. It's just very difficult to add new MIBs, so that's probably not going to last much longer. OpenConfig was another attempt, but the scope wasn't quite wide enough. Ember Plus, again, another great approach, but it's not 100% open. So let's build a 100% open solution and have templates for talking to every type of device that's out there. So quite a bit more work to do, but this is some work that's well underway. It's over a year of effort's gone into that. There's a lot of data in these references at the bottom. These are all available on the AMWA GitHub, by the way, if you want to read some more about these. So the next thing to do is develop all these block specifications for the different types of products. All the protocol stuff has been worked out. Okay, so why should I care about all this? Well, manual device provisioning with typing in a bunch of cryptic IP addresses is just a pain. Nobody wants to do that. It's very error-prone, time-consuming. Plug and play is fun, right? Press the easy button. Let's do it. Let's use a proven technique that makes provisioning new systems much easier. Most all new facilities are specifying NMOS. Most control system providers are fully supporting it. There's one or two laggards, but they're coming around. I've seen some announcements. So, NMOS is what's in most new tenders. How's it going? Well, there were some growing pains early on. and they're due to a variety of reasons. Not all devices supported NMOS early on. You know, they didn't all get through JT&M testing because that was postponed due to COVID, and the controller specs weren't really clear, and there were no real good interop testing. But that's all been fixed now. The mitigation is we do now have JT&M testing. It's back. We have controller testing. We just did face-to-face event at Riedel a couple of weeks ago. We've got this new implementation guide for NMOS controllers and lots of automated tests. So we believe our growing pains are behind us. It's still a lot better than manually setting everything up, but we're definitely getting there. There's testing tools available. You know, I'm running out of time, so I'll go through these pretty quickly, but you can look at the slides later on. You can see links to the Easy NMOS container, which has registries. You can run the testing tools. If you're a product developer, you can run all these tests yourselves, validate your product. You can download Riedel NMOS Explorer, and you can look at your network. And you can see all your sources and your senders and receivers and devices and drag them around. It's a little cryptic, but it works. If you want something a little fancier, Matrox has got a new system called Conduct IP that's a little more plug and play and drag and drop and auto discovers. And this is what we're showing at our booth, by the way. You can come over in Hall 10 and take a look at what we're showing. It's got all the senders on the top and the receivers on the left and normal XY matrix, and we can show you how quickly NMOS routes things back and forth. So takeaways, NMOS is here to stay. It's solid, it's stable, it's mature. Control systems have greatly improved thanks to the interop testing. Some of these new features like ISO 8 audio mapping, system discovery, grouping really take NMOS to a new level, way beyond what SDI could ever do. And now the security is filling a much needed void in the industry to allow us to have secure connections. And finally, NMOS is being extended to be more of the universal control system that it can be. So one ring to rule them all, one API to rule them all. Okay, yeah, so the question is, I'll paraphrase a little bit, how complex would a product implementation need to be to support this NMOS protocol? So it's not too bad that you do need an embedded processor. Usually it's an embedded Linux processor, but it can be a ARM built into an FPGA or can be a separate ARM device. The software is relatively lightweight. It doesn't require a lot of processing power. It's actually being done quite often on embedded soft processors like microblazes or NIOS processors. So it doesn't need a gigahertz processor. It needs a couple hundred megahertz processor. But you do have to have some sort of embedded Linux on each device so that it can respond to these requests. So, okay, thank you.
Thank you, Jed.
Yep.